We now verify that the given trigonometric equation is an identity. So on the left side, we have this expression cotangent x over 1 minus sine x. This is the left side expression. And on the right side, we have this expression secant x times cosecant x plus 1. And this is the right side expression. To verify that this one represents an identity, let's consider the left side expression, that is cotangent x, and this is over 1 minus sine x. First, I'm going to replace this cotangent x using the quotient identity, that is cotangent x basically equals cosine x over sine x. So let's replace it over here, and so this becomes cosine x. This is over sine x. This is the numerator expression, divided by the denominator expression is 1 minus sine x. The next step, we multiplied this expression by the conjugate of the denominator. That is, the denominator expression is 1 minus sine x, and its conjugate will be 1 plus sine x. So we basically multiply and divide by this expression so that we can simplify this. So I'm going to multiply by the conjugate, which is 1 plus sine x, also divided by the same conjugate 1 plus sine x. And so we can rewrite this expression as cosine x, and this is over sine x. Then this gets multiplied with 1 plus sine x. Then we have this 1 minus sine x times 1 plus sine x in the denominator. Let's simplify this. Here I'm going to use the difference of squares formula, that is a minus b times a plus b. This equals a squared minus b squared. Here a is 1 and b is sine x. So let me first write the first expression, that is cosine x divided by sine x, and this multiplied with 1 plus sine x over 1 minus sine squared x. When we use this difference of squares formula, as such a is 1 and sine x is the b. So when we use this formula, it will become 1 squared minus sine squared x, which equals 1 minus sine squared x. And we can now use the Pythagorean identity, that is sine squared x plus cosine squared x equals 1. So if we subtract sine squared x on both sides, we get cosine squared x equals 1 minus sine squared x. That means we can now replace this 1 minus sine squared x as cosine squared x. So let's do that now. So we have the first expression cosine x over sine x, and this multiplied by the numerator is 1 plus sine x, divided by 1 minus sine squared x is cosine squared x. The next step, I can reduce this. We have cosine x here and we have the cosine squared x. So this power 2 will get cancelled. That is, it will become cosine power 1x. Or in fact, we can just write this as cosine x. And so the next step, we write this as 1 plus sine x. We also multiply the sine x with cosine x. So we get sine x times cosine x. Now I'm going to write down this as sum of two fractions. That is, we will have this one fraction, and we'll also have this another term, sin x divided by this one. And so let's write this. So therefore, this is written as 1 over sin x times cosine x, plus the next term is sin x divided by sin x cosine x. Now, the first term can be written as a product of two rational functions. That is, this can be written as 1 over sine x times 1 over cosine x. And for the next term, we see that we can cancel 1 sine x, both in the numerator and the denominator. And so this becomes 1 over cosine x. Remember that 1 over sine x is cosecant x. So I write down this as cosecant x. And also 1 over cosecant x is secant x. This is according to the reciprocal identity. Also, this 1 over sine x, I write down this as secant x. So we have the expression cosecant x times secant x plus secant x, which means we can now factor this secant x from both the terms. And so I write this as secant x times, I factor secant x from here, I'll be left with 1. I put that first, and then if I factor secant x from this expression, I'll be left with cosecant x. So I put that as second. So therefore, we get this expression secant x times 1 plus cosecant x. And in fact, the right side expression is the same. That is secant x times 1 plus cosecant x. Or this can also be written as secant x times cosecant x plus 1. And this is exactly identical to the right side expression. So we have thus proved that this equation represents an identity. We now do question 2. Here we determine the exact value of sine of theta plus pi by 6, given that cosine theta equals negative 3 by 4, where theta lies between 0 and pi. So first we have to construct the right triangle in the quadrant 2, because only in quadrant 2 cosine theta is negative, as well as in quadrant 3 cosine theta is negative. However, since theta lies between 0 and pi, we have to construct this right triangle in the quadrant 2. So here I have constructed this right triangle first and marked this angle as theta. And using this information, cosine theta equals negative 3 by 4, we can mark this adjacent side to theta is negative 3, and then the hypotenuse as 4, because cosine theta equals adjacent side over hypotenuse. And that means we can now find this unknown side, or the length of this unknown side, using the Pythagorean identity. So let's say that this one is x. We determine x, and this equals the square root of the hypotenuse square, which is 4 squared, minus the square of the adjacent side, which is negative 3 quantity square. So therefore, we can solve for x from this. This one is 16 minus 3 square is 9. And so this gives 16 minus 9 equals 7. So we have determined that the unknown side, or the opposite side to angle theta, equals root 7, which I'm going to mark here. This one is root 7. And we know all the side lengths as well as the hypotenuse length of this right triangle. And this means we can write down the sine theta relation, that is a sine theta trigonometric ratio, and this equals the opposite side over the hypotenuse according to the Sokotova. So the opposite side to theta is root 7. This one is root 7 over the hypotenuse is 4. So we have determined the sine theta equals root 7 by 4. And now we can determine this exact value of sine of theta plus pi by 6. For this, I'm going to use the sum formula of sine function, that is sine of a plus b. This equals sine a cosine b plus cosine a sine b. We replace a by theta, so we can expand this using this sum formula, and b by pi by 6. And so we write the expression, or the expanded form of sine theta plus pi by 6. This equals sine, replace a by theta, so sine theta, and cosine of replace b by pi by 6, plus cosine a by theta, and sine a, which is pi by 6. We are going to replace the value of sine theta and cosine theta, also the standard value of sine pi by 6 and cosine pi by 6. So let's put sine theta equals root 7 divided by 4, and cosine pi by 6 is basically cosine 30 degrees, and this equals root 3 by 2. So let's replace that here. This is root 3 by 2 plus us. We then put cosine theta, which equals negative 3 by 4. So I put negative 3 by 4 times sine pi by 6 is basically sine 30 degree, and this equals 1 by 2. So I put 1 by 2 here. Let's simplify this. And so this equals root 7 times root 3. This equals, we can multiply the numbers inside the root and write down this as root 21. This divided by 4 times 2 is 8, minus, we have a minus here. The numerator is 3 times 1 is 3, divided by the product of denominators. 4 times 2 is 8. So here we have the common denominator 8. So we can write down this as root 21 minus 3 over 8. And this is the exact value of sine of theta plus pi by 6.